All right, let's jump right in with a question that feels like it's pulled straight from a sci-fi movie, but believe me, it is quickly becoming science fact.
So, picture this. You're trying to solve a super complex maze. A normal, classical computer, it has to try one path, hit a dead end, backtrack, and then try another, and another, and another. But a quantum computer, well, it plays by a completely different set of rules.
And this visual here really nails the difference. See, while a regular computer is stuck going step by step, trial and error, a quantum computer can somehow see the entire maze, all at once. It explores every single possible path simultaneously. And this isn't just about being faster. It's about a fundamentally new way of looking at a problem.
So how is that even possible, right? Well, it all comes down to the basic language these computers speak. Your laptop, your phone, they all think in bits. They're just simple on or off switches, a 0 or a 1. But a quantum computer, it uses something called a qubit. And a qubit can be a 0, a 1, or, get this, both at the exact same time. And that ability to hold multiple possibilities at once is the secret sauce to everything.
This capability throws us into a whole new game, one that's powered by the bizarre and frankly wonderful rules of quantum mechanics.
So yeah, here it is, the hero of our story, the qubit. Its superpower is existing in all these different states at once, and that's what gives quantum computers their absolutely mind-bending potential. But how does it really work? Well, it's all thanks to 3 fundamental, kind of strange rules of the quantum world.
Let's break down the magic, shall we? We're going to walk through the 3 big quantum rules that make all of this possible: superposition, entanglement, and interference.
Okay, first up we have superposition. This is that crazy ability we were just talking about, where a qubit can be both a 0 and a 1 at the same time. You know, instead of a simple on-off light switch, think of it more like a dimmer switch. It's not just on or off, it can be at any point in between, holding a whole range of possibilities all at once.
This really puts it into perspective. A classical bit is like a coin toss. It's either heads or it's tails. Simple. But a qubit in superposition, that's more like a spinning globe with an infinite number of points on its surface that all represent possible states. And here's the kicker. This power grows exponentially. With just 300 qubits, you could hold more information than there are atoms in the known universe. Just let that sink in for a second.
A really great way to think about this is a spinning coin. While it's flipping in the air, is it heads or tails? In a very real way, it's kind of both. It only picks a side when it finally lands and we look at it, when we measure it. A qubit in superposition is just like that spinning coin, existing in a cloud of probability.
Okay, so superposition gives us this massive space of possibilities. Our second rule, entanglement, connects them in a deeply strange and incredibly powerful way. When 2 qubits are entangled, they essentially behave as a single system. Their fates become perfectly intertwined.
Imagine you have a pair of magic coins. If you flip one and it lands on heads, you instantly know the other one, even if it's on the other side of the galaxy, also landed on heads. That's entanglement. It's this deep, instantaneous connection that lets quantum computers perform calculations that would take a normal computer literally longer than the age of the universe to solve.
This connection was so weird, so counterintuitive, that Albert Einstein himself famously called it spooky action at a distance. He just could not get his head around it. But here's the thing, it has been proven over and over to be absolutely real. And it is completely essential for quantum computing.
All right, so superposition creates millions of possibilities, and entanglement links them together. But how do we find the one right answer in all that chaos? Well, that's where our third pillar comes in, interference. This is the quantum computer's secret weapon for finding the signal in the noise.
Think about dropping 2 pebbles in a pond. Where the ripples meet and reinforce each other, you get a bigger wave, right? That's constructive interference. And where they meet and cancel each other out, the water becomes perfectly still. That's destructive interference. A quantum computer does basically the same thing with possibilities. It is programmed to amplify the waves of the correct answer, while all the waves of the wrong answers cancel each other out, leaving us with the solution. Pretty clever.
So we've got these 3 incredible, kind of spooky principles. But how in the world do you actually build a machine that can harness them?
Yeah, this is definitely not your average desktop computer. This stunning golden chandelier is actually a super freezer, a dilution refrigerator that chills the quantum chip at its very core to temperatures colder than deep space. I mean, we're talking near absolute 0. This extreme cold is absolutely necessary to protect those fragile quantum states from even the slightest vibration or disturbance from the outside world.
What's really fascinating is that we're in the middle of a race to build the best qubit. You've got companies like IBM and Google betting on these super-fast superconducting circuits that need that extreme cold we just talked about. Then you have others like IonQ using lasers to trap individual atoms with incredible precision and stability. This competition is just driving innovation at a breakneck pace, and honestly, it's still anyone's game as to which approach will ultimately win out.
So, we've talked about the how, but what about the why? Why are we going to all this trouble to build these incredibly complex, delicate machines? The answer is pretty simple: to solve problems that we once thought were literally impossible.
The applications here are nothing short of revolutionary. I mean, we're talking about simulating molecules to discover brand new medicines and materials. We're talking about solving mind-bending logistics problems for global supply chains, creating financial models that can see signals hidden deep inside market noise, and even developing a whole new generation of completely unbreakable encryption. And listen, this isn't some far-off dream. Back in 2021, HSBC and IBM actually teamed up to use quantum computing in the high-stakes world of bond trading. The head of quantum tech at HSBC called it a tangible example of how these machines are solving real business problems today.
And this is what they found. It brilliantly illustrates the potential. Their hybrid quantum classical approach showed a 34% improvement in predicting the success of a trade. That is a real, measurable competitive advantage in a massive global market, and it was delivered by today's quantum hardware.
So, while the potential is obviously enormous, we do have to be realistic about where we are right now. We are truly at the very, very dawn of a new era of computation.
Right now, we're living in what's called the NISQ era. It stands for Noisy Intermediate Scale Quantum. A good way to think about it is like the early days of the internet with those old dial-up modems. Today's quantum computers are incredibly powerful, but they're also super sensitive and prone to errors from even the slightest noise in their environment. The biggest challenge for everyone in this field is just making them more reliable. But that brings us to a final and pretty powerful thought. Progress in this field is moving incredibly fast. So the real question isn't if we'll build a fully stable, fault-tolerant quantum computer, but when. We are building machines that operate using the fundamental rules of reality itself. So what happens to science, to medicine, to our entire world when that noise finally fades away?